Before discussing or defining the group, we'll define binary operation. Suppose G is a set, then by a binary operation star, we mean a map from G cross G to the set G itself. Let us take an example. Suppose we have the set of integers and addition is a operation. It's a binary operation. Because suppose if we take two elements, say a b in Z, then a plus b is also in Z. So basically addition or plus is a mapping which maps to a plus b. Second, a binary operation is called associative on a set, say G itself, if for any three elements in the set G, suppose star is the binary operation, similarly a commutative binary operation on a set G, star is the binary operation, say star, the binary operation is said to be commutative on the set G if for any two elements in the set, if x star y is equals to y star x. Okay, so let us see some examples. Suppose we are taking the set of integers. Then addition on the set Z is commutative because 2 plus 3 is equal to 3 plus 2. So for any two elements in Z, a plus b is equal to b plus a. Similarly, addition is also associative because we know addition in real lines in integers is associative. So now we will define group. A group is an ordered pair G comma star, where G is a set and star is a binary operation. Okay, this ordered pair is said to be a group if it satisfies the following three axioms. Axiom number 1, the binary operation star is associative. Axiom number 2, for all elements of the set G, there exists a element E in the set G such that X star E is X, is E star X. That is, there is an element which is, when multiplied with the element, gives the same element. And third, for all X in the set G, there exists element, say X inverse, in the set G such that X star X inverse is the identity, that is X inverse star X. So in order to check whether a ordered pair is group or not, we need to check basically 4 things. First of all, we need to check this operation is whether binary operation or not. That is, we also have to check for all A, B in the set G, A star B whether belongs to G or not. So we need to check this. So this property is called closure property. We have to check whether star is associative or not. That is, any 3 elements X, Y, Z, whether they satisfies associativity. Right? We have to check whether every element has a identity element. This element is called identity or not. And we have to check for every element in G whether there is a element, inverse element, that is called inverse. So let us see some examples so that would be much more clear. Again we take integers under addition. First we see that closure. We know for any 2 elements A, B in integers, A plus B will also be an integer. So closure property is satisfied. Second, we have to check associativity. Now in Z we know that it's very trivial because addition in Z is associative. Third, we have to check whether it has identity or not. For all A in Z, we know there is a 0 element in Z which when added to a element gives the same element. So 0 is the identity. Now we have to check inverse. Look that for all integers there is a negative of that integer which is called the inverse, such that A plus minus A gives the identity. So Z plus is a group. Similarly, real line under addition, R plus is group, C plus is group. Let us see a question. Suppose Z plus is all integers including 0. Then whether this operation is a binary operation or not. Clearly, suppose if we take two elements 1 comma 2 from z plus, then under this operation 1 comma 2 will be 1 minus 2, that is minus 1, that does not belongs to the set of positive integers. So this is not even a binary operation. Let us see another example. Suppose we are having the set of integers and we are defining an operation. If AB belongs to Z, we are defining an operation star AB is like this: A plus B plus AB. So we have to check whether this is a binary operation, and we have to check whether this is associative binary operation or not. Firstly, we look that addition is a binary operation. So if we add two elements in Z, then that will be also in Z, and if we multiply two elements in Z, that will also be an integer. So basically any two integers will be mapped to an integer. So this is a binary operation, no doubt. Now we have to check the associativity. So suppose x, y, z are three elements in Z. Now we shall calculate this element. So x star y will be x plus y plus xy star z, right? So this will be right. So this will be so basically this will become x plus y plus z plus xy plus yz plus zx plus xyz. If we again calculate the term x star y star z, then this will also be equal to the same term. So we can claim that this operation is a associative binary operation. Let us conclude this lecture with a question. Suppose we are defining a set G such that x belongs to R and x is a fraction. X is a number in between 0 and 1, which may include 0. And we are defining an operation. Suppose AB belongs to Z, we are defining operation A star B is fractional part of A plus B, that is A plus B minus A plus B. Now the question is, prove that this is a group. So let us see how many of you can prove this. So try to prove this.